Hello and welcome to MT3. This is Eigenvalues and Eigenvectors. Now we are in part 3 of the recordings of this particular topic. Alright, because it's rather complex, so I'm splitting it up into multiple parts. Now in parts 1 and 2 we have looked at the properties of Hermitian operators. I've given you exercises dealing with the properties of other kinds of operators, anti-Hermitian, unitary, etc. And now we're going to look at a more general case. We're going to look at normal operators, normal matrices. Now just to remind you, a matrix A, a square matrix A, is said to be normal if it commutes with its adjoint. So if A dagger is equal to A dagger A, then it's a normal matrix. You can write this in operator form as the operators commuting, the operator commuting with its adjoint. Okay, so every just to remind you again, every operator has a matrix form once you introduce a basis. Now Riley, Hobson and Benz are going to prove some of these results using the matrix form. I'm going to show you the proofs using the operator form. And I hope you will go and look back at Riley's book and see that there's a one-to-one mapping between every step in these proofs. Now to remind you again, Hermitian, anti-Hermitian, unitary, anti-unitary, orthogonal, symmetric, anti-symmetric matrices, they are all examples of normal matrices. And if you haven't shown this and convince yourself that these are in fact special cases of normal matrices, then this is where you need to do it. So before going any further, I would like you to actually show these, take 2 or 3 of these cases and show that they are special examples of normal matrices. Now everything I'm going to be talking about is in Riley, Hobson and Benz 8.13.1 and subsequent sections. Okay, so what I'd like to show is that the eigenvalues of a Hermitian matrix, of the adjoint of a normal matrix, are complex conjugates of those of the matrix A. Or in operator form, what we want to show is that if we have so let's write this down actually. So what I want to show is that if we've got an operator A with eigenvalues x and A is equal to lambda, A operating on x is equal to lambda x, then A dagger operating on x, in fact they will share the eigen vectors, the eigenfunctions. This is going to be equal to lambda star x. So that's what we want to show. Alright, so now let's start. So let's start with one of these equations here. This is the first one. So we know that A operates on x, and that gives us lambda times x. Now what I want to do is to bring these two to one side, and this looks a bit funny because I've got an operator operating on a function here, and then I have a scalar here. Now what I can do is stick in another operator. Which operator can I stick in? Well, I can stick in the identity operator, because the identity operator operating on a scalar, operating on any vector, gives you the same vector. Alright, so we can do that. Now we can bring these two together, and then we have therefore A minus lambda I operating on x. Now we've got operators in both terms. That's equal to the 0 vector. Okay, remember when you it's not 0, it's a 0 vector that appears here, because the result of this is still going to give you a vector. Alright, so that's good, but some books just call this 0. It won't matter much here. Okay, now what we're going to do is take the norm of this. So just to remind ourselves, the norm of any vector A is the square root of the inner product of the vector with itself. So what I want is actually not the norm. I'm going to take the norm squared, and that's going to give me just this thing here. Now because this whole thing evaluates to the 0 vector, so if I set a is equal to this, then the norm squared of a will be the norm squared of the 0 vector, which is going to be 0. All right, so let's take this vector, and to get the norm I have to take the inner product of this whole thing with its adjoint. So what we end up with then is the adjoint of this part here is x a hat minus lambda I hat dagger. Remember, when you take the adjoint of something, you take the adjoint of each term, but you reverse the order. A cat becomes a bra, and this is an operator that gets adjointed out here. Okay, so then we have this is the adjoint, so that's the bra side, and now we have the cat, which is here, and that will be a hat minus lambda I x, and that's equal to 0, so let's put the 0 over here. All right, now what we want to do is to expand this product of operators. So only this is going to be equal to, first of all, we can take the adjoint in, so this will be a adjoint minus lambda I. Now what happens to lambda when you apply the adjoint? Well, let's put the adjoint over here. This is an operator, and then we have a minus lambda I. Okay, so this is, now a is not Hermitian or any such thing, so a dagger remains a dagger. When the adjoint operates on lambda, it's a scalar, so it just gets complex conjugated, so we'll have a minus lambda star. Now I is the identity operator, and the identity operator doesn't get affected by the adjoint. I would ask you to show this. All right, so this remains I hat. Now one way of seeing this, by the way, is the identity operator in matrix form is the diagonal matrix with ones on the diagonal and zeros everywhere else. When you take the adjoint, you take the complex conjugate and transpose of this thing, it remains the same. And this is one way of looking at it. From the matrix point of view, it's pretty obvious that nothing's going to change here. All right, so that's the left-hand side. Then the left-hand bracket. Then we have a hat minus lambda I hat, and now we can cross multiply. We have a dagger a minus lambda a dagger I minus lambda star I hat a plus lambda star lambda I hat I. Now the identity operating on the identity gives us the identity, but it doesn't really matter at this stage. We'll just leave it as it is. Now what we want to do is use the property of the normal operator. If a is a normal operator, then this is equal to a dagger. Okay, so what that lets us do, and I'm going to skip a bit of algebra here, what that lets us do is effectively now reverse these two terms, sorry. Here we've got the adjoint on the left hand side, and then you have the operator without the adjoint. Now because we can make this swap, I'd like you to show that what this gives us is okay, just pausing this here. Okay, to see what's going to happen next, now let us define one of these matrices, one of these operators to be B. So now I'm going to define the operator B is equal to A minus lambda I, there's a hat here, dagger. Therefore, A minus lambda I itself, which is on this side, is simply equal to B dagger. Why? Because when you take the dagger of B, you will have a double dagger here, and that means you're complex conjugating twice, which means you remove the complex conjugation, and you're transposing twice, which means you flip the rows and columns once and then you flip them back again. So in other words, B dagger is equal to this part here. Okay, so this thing then is equal to B operator dagger times B. And now we can put it all back into this expression here. Therefore, 0 is equal to x B operator dagger B operator x. Okay, and this, if you look at it now, this is the inner product. This is the norm squared, sorry, of B operating on x. Yeah. Let's go back to the definition of the norm squared. The norm squared is simply norm squared of a vector here is simply the inner product of the vector with itself. So the norm squared of B operating on x, this B operating on x gives you a vector. This is the norm squared of that vector. This is now equal to 0. Therefore, the only way this can happen that the norm squared of a vector is equal to 0 is if the vector itself is 0. Or the 0 vector. Okay, now we can pull this dagger in. The dagger operates on the A. Then you have a minus. It complex conjugates the scalar here. It does nothing to the identity. Or A dagger operating on x is equal to, if I pull this on this side, lambda star I hat operating on x. And now we can drop the identity operator because it's not doing anything anymore. Therefore, we have proved our result. Oops. A hat dagger has eigenvalues lambda star. So the eigenvalues are the complex conjugate as those for the operator A. Now, if this looks a little complicated because we're using the Dirac form, what I'd like you to do is to go to Riley, Hobson and Benz 8.13.1 and have a look at how they do exactly the same proof but using matrices and vectors only. Okay, and see if you can, in fact, it would be a very good exercise if you can match up their steps with the ones I have shown you here. Okay, now there are a couple more results I need to show you. I'm going to have to write them down and then come back. So let's pause this again. Okay, back again. Now I'd like to show two more results before stopping this this kind of recording. The first is that if A is a normal operator, then its eigenvectors corresponding to different eigenvalues are orthogonal. Hey, that sounds like the case for Hermitian operators, and in fact, if you prove those results for anti-Hermitian operators, etc., Here we're going to show that it's the case for normal operators. Now, because Hermitian operators, unitary operators, etc. are all examples of normal operators, then this result, in fact, is the more general result, because it then proves the same thing for all of those classes of operators. The next is a rather unusual result, which says that the operator A can be written as the sum over its eigenvalues lambda times the ket bra. Now this is the outer product. Remember, we have seen this before. This is the outer product of xi with itself. Or in matrix form, the matrix A is equal to the sum lambda I, the vector xi times xi dagger. Now each of these products is going to give you a matrix. So what we are doing is we are decomposing A into a sum of matrices. Alright, now let's see, we'll prove these in turn. First, the first result. Okay, so result 1. Oops. 1. Now how do we show this? Well, let's start. So A is normal, therefore A dagger is equal to A dagger A, and if we have A if A xi is equal to lambda I xi, then let's remind ourselves, then A dagger xi is equal to lambda I star xi. Okay. Alright, now we need to show that the eigenvectors corresponding to different eigenvalues are orthogonal, so we need two of these cases. We need the eigenvalue equation for xi and for xj. So let's consider two of these. This is the first one, so let's write it down again. A xi is equal to lambda I xi, that's 1. And the second is A xj is equal to lambda j xj. And we are also told that lambda I is not equal to lambda j. Okay, so let's take one of these equations and do the same kinds of operations we did when we showed this result for Hermitian operators, and let's see what we get. So take 1, we take the adjoint of 1. Alright, that will give us, remember what the adjoint does, it converts the kets into bras and changes the order. Everything gets adjointed, but you change the order. So 1 becomes xi, that becomes a bra. Then we have the adjoint of the operator A, and that's equal to, now here we get the lambda I gets complex conjugated because it's just a scalar, and then we have xi bra. And then we do the obvious, we take the inner product with xj. With the ket xj. Alright, so this gives us xi A dagger xj is equal to lambda I star xi xj. Now A dagger operating on xj, now we know that A operating on xj gives us lambda j xj, and we know that A is normal, therefore A dagger operating on xj, so since A is normal, Therefore, a dagger operating on xj is equal to lambda j star, the complex conjugate of this xj. So we can use that. Therefore, we get xi lambda j star xj is equal to lambda I star xi xj in a product. Now lambda j star can be thought of as being on the ket side because it's in front of the ket, and what we can do then is move it out completely without change. That gives us the inner product of xi with xj is equal to lambda j star times the inner product of xi with xj is equal to lambda I star times the inner product of xi with xj. As with the Hermitian case, we're going to bring these two terms to one side, and that gives us lambda j star minus lambda I star times the inner product with xi and xj is equal to 0, and that's the 0 number, not the 0 vector. Now, if lambda I is not equal to lambda j, then lambda I star is not equal to lambda j star. Therefore, lambda j star minus lambda I star is not equal to 0. Therefore, we must have xi, the inner product of xi with xj is equal to 0. That proves the result we had here, that if A is a normal operator, then its eigenvectors corresponding to different eigenvalues are orthogonal. Now, what about the case when the eigenvalues happen to be the same? We do exactly what we did for a Hermitian operator, and we use Gram-Schmidt orthogonalization. I've explained this over here. We can form linear combinations of these eigenvectors. We can then use Gram-Schmidt to orthogonalize them, so that in general, even for a normal operator, it turns out that the eigenvectors of a normal operator can be will either be automatically orthogonal, that's if they correspond to different eigenvalues, or they can be made orthogonal if they have the same eigenvalues, that is if they are degenerate. They can be made orthogonal using the Gram-Schmidt orthogonalization process. Okay, so that's the generalization of the result for Hermitian operators. This now holds for normal operators, and because it holds for normal operators, this result holds for Hermitian, anti-Hermitian, unitary, anti-unitary, orthogonal, symmetric, anti-symmetric. All of these cases follow, and that's the nice thing with dealing with normal matrices. We get a very general result. Now the next thing I'd like to show is quite a surprising result. This is this one here, that we can write a normal operator or a normal matrix in terms of its eigen values and eigenfunctions in this form. So what we're going to show now is, so that's number 2, I believe, to show that A hat is equal to the sum I goes from 1 to n. Remember, n is the dimension. N is the number of eigenvectors you're going to find in this space. Yeah, and you will so n is the dimension of the space, and then we have lambda I, and then we have the outer product of xi with itself. Or in matrix form, we write the matrix A as the sum I goes from 1 to n, lambda I, the vector xi, times its adjoint. Oops, I think I need a parenthesis for this. Otherwise we have two operations in the superscript. Right, we're going to show this. Now what we're going to do is I need a couple of results before we can show this. Now we had argued that so from the previous result, we know that the eigenvectors of a normal matrix will either be orthogonal or they can be made orthogonal. Therefore, they can, so in general we're going to assume that these eigenvalues, eigenfunctions are orthogonal, and if they are orthogonal, and because there are n of them, they can form a basis for the space. So the first thing I'm going to be needing is the eigenvectors or eigenfunctions of A form an orthonormal basis. Okay? Now what that means then is if I have any vector y, I can write this as a linear combination I goes from 1 to n of some coefficients ai times these basis vectors xi. Alright? Now what I need to show is that if I operate with a hat on y, I need to show that I get the same result if I operate with this side. Now I've got a sum over I here and a sum over I here. I don't want to have these sums the same, so I'm going to change one of them to a sum over j. This is quite important and you should not forget it. Okay, so what I want to show now is that if I replace a with the right hand side, then I get the same result. And if this result holds for any vector y, which is written in this form, because this is the general form, then it holds in general. Therefore, we will have an identity. That's what we are going to do. Yeah. So that's the idea, right? We're going to show that this holds for any vector y, and therefore, if it holds for any vector y, then this a hat must be equal to this stuff in the parentheses. Okay, so let's take the LHS. That's simply a hat operating on y, but we know that y is given by this quite generally because these eigenfunctions, these eigenvectors of a hat form an orthonormal basis. So it's a complete basis for this space. Okay, so then we have a hat operating on the sum. J goes from 1 to n, aj, xj. Now a is a linear operator, so it can be pulled into the sum, and it does nothing to the scalar there, it just operates on the vectors. So we'll bring the sum out. J is equal to 1 to n, aj, and then this operator operates on the vectors. Now a operating on xj gives us, we know what it gives us. It will give us a lambda j times xj. So we know what the LHS is. The question now is, what is the RHS? So let's have a look at the RHS. That's equal to this sum operating on y. So that is the sum I is 1 to n, lambda I, xi, this is the outer product, this whole thing operating on y. Okay, Now let's see what this does. So this is going to be the sum I goes from 1 to n lambda I xi. Now this is simply going to join up with this to give us the inner product of xi with y. But what is that? Well, let's see. So I'll draw a line here. We know that y itself is given by this linear combination of the xj's. So let's use that. xi y is equal to, that's the inner product, so that's xi, the inner product of xi with this sum j goes from 1 to n of aj xj. Now this is a linear combination of vectors, and we know from the definition of the inner product that if you have the inner product of a vector with a linear combination of vectors, you can write it as the linear combination of inner products themselves. So you can bring out the sum. That's why everything is nice when things are linear. Now these a's are in the ket side, so when we bring them out, they stay unchanged. No complex conjugation. And we have the inner product of xi with xj. But this forms an orthonormal set. So this is delta ij, the Kronecker delta. Now remember what it does from the recordings on index manipulation. The Kronecker delta collapses a sum and it sets the dummy index, which is j. Remember, j is dummy because I'm summing over j. So the only non-zero value of the Kronecker delta will be when I is equal to j, or j is equal to I. In that case, you will get a 1 from here. In all other cases, you will get a 0. So when you get a 1 from here, you will end up only with this thing ai. Okay, so this then gives us, so that's an aside. This will give us the sum I goes from 1 to n, this is an I here, of lambda I xi, and this gives us ai. Now we should not be surprised here. Oops. Because if we go back a few of these recordings, and I can't remember which one it was in now, we showed that these expansion coefficients, when you have a vector y and you expand it in a basis, the expansion coefficients are defined to be the inner product of the basis vectors with the vector y, which is exactly what you've got here. The inner product of the ith basis vector with y is the coefficient of expansion of that particular vector. So this is equal to I is equal to 1 to n ai lambda I xi. And now if you compare this to the left hand side, it's the same thing. Remember, this is the sum over j, this is the sum over I, but I and j are dummy indices. They are both summed over completely. So these two sums are the same. That's equal to the LHS, and this holds for any vector y. Therefore, in general, any operator A can be written as the sum I goes from 1 to n of its eigenvalues times the outer product of its eigenvectors. Great, right? I mean, any normal operator. Now, because it applies to any normal operator, this applies to any Hermitian operator, any unitary operator, etc. It just goes on. Cool, huh? Now, here's something interesting. I'd like you to try this out. Show that the identity operator I hat can be written as I goes from 1 to n of xi, the outer product of xi with itself. So if these xi's were the orthonormal basis of eigenvectors of some normal operator, then the identity operator can be written as this sum. Okay, I'm going to put a box around this, and I'd like you to show it. It's quite a nice exercise. And this is so important that this combination, whenever you have a complete basis of orthonormal vectors like this, you take the outer product in this form. Each of these multiplications, by the way, when you represent these as vectors, each of these multiplications will give you a matrix. You add those matrices up, you will get the identity, which is the diagonal matrix with only ones on the diagonal. And this happens so often that we call this, now this is looking beyond MT3, we call this the resolution of the identity. We are resolving the identity into components, and each of these components is based on the outer product of two eigenfunctions of a normal operator. Okay, I won't say more about this, but you probably will see this in advanced quantum courses where we make heavy use of the resolution of the identity. In fact, once you've understood how it functions, it can be used to simplify proofs quite enormously, and it's quite an elegant way of using this for proofs. Now, when I use it in my own work, these sums are infinite sums, and it's quite nice to see how the infinite sums come in and how they can be used with this relation. So please show this. Yeah, so I'm going to stop here, and the next topic we're going to be covering in a separate recording will be related to how we, this is just the algebra. This is all the ins and outs of the algebra of eigenvalues, eigenvectors for these particular kinds of matrices. Next, we're going to see how we actually find the eigenvectors and eigenvalues of a matrix, and then we'll come back to these results and see if they actually hold. Of course they will, but we'll see how they actually hold for particular kinds of matrices. Okay, so we're stopping here. Thanks for watching.